Okay, okay, James, you can go.
Well, thanks again, everyone. I am really bummed that I couldn't make it there, but hopefully we're all successful in finding funding to continue meeting up into the future. And thanks again to all the organizers. Please tell me if it's worth calling in for a discussion later. But from the agenda, it sounds like this is the last time I'm chipping in. So feel free to interrupt and ask questions as I go. I think I have half an hour, and I wanted to cover 3 different topics related to methods for distribution shift. And some of these same methods will be applied, I think, or discussed later in the context of spatiotemporal variation in either weight at length, condition, body condition, or length at age. But I'm still focusing on sort of biomass dynamics, and focusing on distribution shift. And I wanted to talk today about ecosystem modeling, attribution, and skill testing. So, my stump speech these days is that, the field of stock assessment, at least, historically has been focused on, harvest policies, long-term, strategies, quota setting, and so forth. Our field also has habitat assessment, integrated ecosystem assessment, and climate assessment activities that we're legislated to do in the U.S. And all of these have a different audience with a different set of, questions and a different access to, legislative priorities. I think these different methods have grown up kind of different ways of addressing their questions, different models. And my hope is that we can try to come up with a unified approach to all these different activities. And I think the benefits of that would be that, doing this as a spatiotemporal model at least, is that we can include biological mechanism. A lot of theory pertains to, individual scale decision making. Hopefully we can improve communication both within our field and outside our field. And hopefully we can end up with similar, review standards and burdens of proof. Across these different activities. And, I'm not the first person to say this, like Walter Jett's in the Map of Life project in the terrestrial world. I think he came, there's the Darwin core, and then I think Walter came up with the Humboldt core. And terrestrial biogeography has has similarly made this claim that, local density of one of multiple species across space and time is a common currency that can be then used to, then converted to habitat, ecosystem, population, or climate assessment. And so this is, visualization of a map of Pollock and Eastern Bering Sea. If you walk in, I think this, show this to stakeholders. I think you get further than a time series. And again, you can back out a lot of things that are happening in this stock. When I was asked to talk about methods, I assumed that we weren't really meaning computational methods as much as sort of analytical or, ecological methods. But, the big picture view is that, a spatiotemporal model defines a spatial domain. So on the left-hand side, we've got 10 blue numbered locations. The methods I'm using define a triangulated mesh, and then use methods for finite element analysis to look at, basically solve for a partial differential equation, linking those different locations. And there's some, interesting math that has come up over the last 10 years about how to efficiently, equate a partial differential equation to a spatial process. So in the following, I'll be using a Materin correlation function, which is the red line on the right. And that's, again, comes out as a solution to a partial differential equation defined for a set of locations within a spatial domain. And so this spatiotemporal modeling approach tracks density for multiple species across space and time. I kind of concluded that, that not everybody's going to want to build their own software to do this. So at the same time, I've been building this R package called VAST for Vector Autoregressive Spatiotemporal Model. At this point, it's been used in 19 stock assessments, or in base case, or as alternative models, 2 ecosystem status reports. It's mainly focused on the Pacific, although it has been used for stock assessment in South Africa and the Gulf of Maine, and it's seeing more use in other tubic missions. And the main features is that it's a multivariate model, so it can do all the kind of community analysis using multivariate modeling. It can be used as a simulator, so generate data. You can assimilate multiple data types, so presence only, presence absence count, and biomass sampling data at the same time. And it includes features for seasonal modeling. And I actually didn't count the number of papers, but it's well over 20 that have used it by now. So hopefully there's some shared, some benefits in sharing development costs. Although the Alaska Center is also still trying to have multiple models to do all these things, to compare between them. So the 3 things I want to talk about today, one was ecosystem modeling, and I'll explain why I think that's important. And then causal attribution and skill testing for short-term forecasting. So these are, the latter 2 are especially relevant, I think, to, the questions in the working group. But first I'll talk about spatial temporal models of intermediate complexity, or, Eva Plagiani calls these mice models. And, so I'm calling this a mice in space model. And I've been developing this with Kirsten Holzman at, the Alaska Fisheries Summit Center, and Grant Adams, who's a great PhD student at University of Washington. So the question in this is, how do you unify analyses for ecosystem dynamics and for spatial management? And the idea is to extend the VAST package to include ecosystem dynamics, so including fishing mortality, species interactions, and biological reference points. And, the VAST basically tracks 2 different linear predictors. So in this case, in all of these kind of more mechanistic analyses, it tracks numbers density, or abundance density, n for every location S, category T and category C and time T. And then it also tracks biomass per individual, W for every location S, category C, and time T. So the product of these 2 is biomass density. Given those 2 different quantities, you can fit to presence only, presence absence count, or biomass sampling data. And the biomass sampling data is essentially a delta model using this Poisson link that I published last year. So if you as a case study, I fit this to data for 4 species in the Gulf of Alaska. And if I fit it as an index standardization model, so a separate intercept for every year for every species for the 2 components, or I fit it without interactions, but density dependence within each species, or I have separate density dependence within each species, or I fit it with species interactions between species. The species interactions model ends up the most parsimonious based on AIC. So you can if you properly specify a model, this model selection has some meaning, as I think it does here. All 4 of these different models are shown for the 4 species on the right-hand panel. So in this case, and then each panel shows a dashed line showing fishing mortality rates. And all 4 models estimate about the same trends in biomass, and all can interpolate what's happening in years that aren't sampled. The Gulf of Alaska's only been sampled every 3rd year and then every other year. And so, specifying a model for this allows you to interpolate between sampled years. If we look at this across space, kind of in the way that I think is more useful to communicate to stakeholders and also can be used for spatial management, we can back out what's the unfished biomass B0, or unfished biomass density, sorry, for each species. And it shows that, Gaddis calcogrammus, pollock has these hotspots near Kodiak Island. Aphorestes stomaeus, the arrow-toothed flounder, seems to have, highest density inshore of Kodiak Island, and so forth. And then you also get estimates of biomass density. Here I'm just showing them for evenly spaced years for each species, and you can see hotspots winking in and out for each species. So again, this is something that you could walk in and present to the fishing industry, but it also, obviously, all of this can be backed out to look at distribution shift. The model estimates fishing mortality targets from an estimated interaction matrix. And so each of these different models estimates a different fishing mortality target, F-targ, and a biomass target, E-targ, using standard proxies. And the biomass targets are pretty similar. The fishing mortality targets differ more between models. And then using the selected model, you can back out status, so these stock status plots on the right. So again, this sort of multi-species spatiotemporal, mice in space model can get it can back out all of your reference points like we use in stock assessment. We also can use it as an operating model, so if we fit to these data and then simulate new dynamics for each of the 4 species given the estimated parameters, and then we can fit another model to dynamics, simulated data from the 2 of the 4 at a coarser spatial resolution, and compare those resulting fits with what we knew to be the truth in the operating model. And we can use that to test our, in this case, estimation model, but you can also use it to test a management procedure or some technique for causal attribution. And in this case, comparing the first and second row or the third and fourth row, you get similar estimates of density for the, even when neglecting 2 of the 4 species. And then finally doing this to look at estimates of interaction strength between species. There's a 2x2 interaction matrix that the model is estimating, and the histogram shows the estimates across 100 replicates. Maybe it's 50, I forget. But it's approximately unbiased for estimates of interactions, even when neglecting some of the species in the community. So again, the relevance for this, well, partly I put it in just because I wanted to walk through a little bit about the kind of multivariate modeling piece. But it also can be used for attribution, and it's a structural model that can be that can include fishing mortality, species interactions, and covariates like climate. And so once you have all those in, you can fit the model and explore the relative importance of those different structural elements. It's also an ecosystem model that includes center of gravity, so we could use it for for backing out ecosystem modeling skill for looking at distribution shift. And then finally, it can be used as an operating model in a simulation experiment. So I've already brought up climate attribution a bit. I want to use this term of attribution because it's it's used by the, for instance, in the kind of extreme event like, weather attribution, hurricane attribution literature. It's also used widely in, in econometrics and health metrics, where they do big studies and they want to figure out, what proportion of, a decrease in child mortality is due to some intervention versus due to other extraneous features. So I think that attribution is what we're basically called to do by the International Panel on Climate Change when they ask for, probabilistic statements about the impact of different climate, RCP scenarios. So I'll be presenting some work I published last year with Jim Yanelli and Stan Kowicki, who are both at the Alaska Fisheries Science Center. And in this case, we fit to Pollock, like we saw in that first slide. We fit a size structure model in this case. So, a multivariate model that doesn't have any explicit growth dynamics, but does fit, expected spatial distribution of each of these 5 different size classes. And there is, like in this species, like many species, there's ontogenic habitat, partitioning. So the spatial distribution of adults is different from juveniles. That makes sense for any cannibalistic species, or anything where there's differences in productivity spatially. And we also put in, local and regional temperature impacts. So, and then also there's this unexplained spatiotemporal variation. And so there's essentially 3 different mechanisms that can be used to explain distribution shift in the species that are included in the model. And so that leads to 3 different counterfactuals that our structural model can generate. We fit the model with all three mechanisms, and then we can turn off everything except temperature and look at the isolated effect of temperature after accounting for the others. Or we can turn off everything except recruitment variation and size structure differences in expected habitat, and look at how much the differences in size structure over time explain distribution shift. Or we can turn off both of those two and just look at residual variation. And so if we do that and we plot out density resulting from, well, all of those mechanisms together on the left-hand column, or just temperature and isolation in the second column, or just size structure, or just the unexplained component, you can already see that size structure and temperature do not explain, they explain kind of the fundamental niche, the kind of average distribution for this stock, but it doesn't explain that much of the interannual variability, at least when fitting, conditional on the model structure and only fitting through 2015. And again, so each of these counterfactuals, we can back out the center of gravity for the total biomass or for each size class. And for instance, size structure, each of the size classes in this size structure only have the same distribution across time, but the relative composition of different size classes leads to some variation in the total abundance in that size structure in the third row. Temperature and isolation leads to some variation, but the long-term secular trend of about 200 kilometers north over this period, is not explained by either temperature or size structure and isolation. And again, I think this is sort of a pretty contrary conclusion about Pollock. I'm aware that temperature drives the distribution of larvae, and the cold pool is clearly a mechanism for impacting distribution of pollock and many other groundfishes. But I'm not confident that the impact of cold pool has been the same across this entire time period. So, maybe you could get a better temperature model if you break it into, impacts, prior to the 2000s versus after, so you could dial in some of these models and explain more variation. But in general, for kind of global comparisons, we don't end up with highly stock-specific models of temperature impacts. Okay, so the conclusion, temperature generates some north-south variation, recruitment generates some east-west variation, but the majority of distribution shift is not explained by either of those on average across the 30 years. This is all before the 2015 onset of rapid warming, and it doesn't include the northern Bering Sea footprint. So there's more work that could be done, but hopefully this illustrates what I mean by attribution and why we would care. And then finally, I wanted to talk a little bit about forecast skills. So I think as a community, when people started publishing analyses of distribution shift maybe in the mid 2000s, people could publish a model in a small journal and then use it in subsequent science papers, but at this point we actually have a lot of different models we can use to both identify distribution shift, to attribute distribution shift, and to forecast it. And so at this point, I think as a community, we should really shift to trying to determine which of those methods are working well, at what spatial scale, at what temporal scale, for what question. And I think the way to do that is using, evaluating forecast skill. That's the term that, physical oceanographers might use. Specifically, the IPCC, again, wants us to make, wants us and every, ecological community to make probabilistic statements, like that climate impacts are extremely likely or probably causing, X% change in productivity. And I don't think we can honestly make those probabilistic statements unless we have models that have been, shown using skill testing to have good performance probabilistically for forecasting. So again, how do we best forecast changes in distribution? Well, The obvious way to do that is to fit the model to historical data. So in this case, using the Eastern Bering Sea, fit it from 1982 to some final year, predict future changes in the center of gravity or center of distribution 1, 2, or 3 years out, compare that with a perfect persistence forecast that says that there's no changes after that final year, and then compare that with subsequent observations of changes in the distribution. And to showcase this, I use data from 20 species in the Eastern Bering Sea bottom trawl survey. And I'm going to compare 3 different methods. One of them is the climate envelope model. So I think Morley has a paper recently in +1 that forecasted distribution shifts for about 600 species using a climate envelope model. I forget if that's the same one that Malin's also been talking about. Malin published one recently as well. In this case, I have a very simplified climate envelope model that has temperature and temperature squared impacts on those 2 linear predictors. William Chung, since the 2000s has had essentially kind of a climate envelope model as far as I can tell. That also includes, local density dependence and some other features, but it's a similar concept. The third method is an annual regression. So Steve Hare and others, John Hare and others have calculated the centroid each year and then regressed that centroid against annual covariates, and then use future values of those covariates to forecast shifts in the centroid. So like Janet Nye and Grant Adams have gone back and forth about whether temperature fishing is driving shifts in the Northwest Atlantic using that annual regression method. And then finally, you can use a spatial temporal model with or without temperature. And so those are the 4 models I'll be looking at. And if you do this for pollock, for instance, the climate envelope model, when you fit it to data, subsequently update it with data, it doesn't make that much of an impact on historical estimates. The parameter values are pretty constant over time, and it also misses the northward shift. That's sort of what we saw before as well in the last one. The annual regression shifts more over time, and it does a better job. It's more correlated, but it still misses the northward shift over time. In this case, regressing against cold pool size. And then finally, the VAST model with or without temperature obviously captures historical estimates pretty well. When it goes into forecast mode, it reads off the estimated autoregression across time, and it is mean reverting. The subsequent years are shown in red versus blue for early years, and later years it forecasts to a higher average center of gravity. It also has much wider forecast intervals, so that sort of cone, I think they call it like a cone of uncertainty in hurricane forecasts. And that cone of uncertainty really should, ideally should represent, true forecast uncertainty if it's going to be useful for managers. And so if we do this and then we measure forecast skill relative to a persistence forecast, so it's a measure of how much of the variance is explained in future distribution shift. A negative value means that it does worse than a persistence forecast, and a positive value means it does better than a persistence forecast, where a value of 1 would mean 100% of the variance is explained, a perfect forecast. And this very simplified climate envelope model does worse than a persistence forecast. It is correlated with distribution over time, but it does worse than for predicting future changes than if you just predict that the next year is identical to this year. The annual regression method explains 2 to 6% of variance, and the spatial temporal model explains 8 to 25% of the variance. So, I do think that 8 to 25% is sufficient, improvement on a persistent forecast that we could use it for short-term fisheries management. And we can come back to that. Finally, if we look at the quantile for observed shift in distribution given the predicted distribution, a well-behaved model will have this empirical quantile be uniform. That's what the definition of a well-behaved quantile. And the VAST models have approximately a uniform distribution. Certainly compared to the other ones that have most of the density piled up at 0 or 1, representing that they have a forecast interval that's much too small. So again, that climate envelope and annual regression not only are kind of missing the story in some cases, but they're underestimating their own uncertainty when forecasting and giving a false appearance of certainty where we shouldn't trust that we have one. So finally, my take-home message is, well, we can build ecosystem models that are spatially explicit, that can be used for both estimating historical distribution, for simulating data to test different estimators, and for exploring different policies that could account for distribution shift. I think climate attribution is a direction that would be good to go in because it uses the same vocabulary and the same methods as health and econometrics. It links up well with the vocabulary of the IPCC. And the path to that is building structural models that include multiple mechanisms for distribution shift, and then essentially turning off one or the other to isolate the effect of a given mechanism. And then finally, my claim is that I think we need to be more careful as a community about reviewing and trusting advice from models that have not been demonstrated to have good skill. This is essentially like Mone's Rho, or retrospective bias is a commonly used method in stock assessment to determine if a model is performing well. And I'd love to see that same retrospective skill testing applied, within the climate attribution and climate forecasting literature. So thanks again to the organizers, and maybe I have a couple minutes for questions.
Yep. So, I'll get the microphone here. I have a really quick question. Maybe I missed this, but how in the vast model without the temperature, what was the forecast actually based on?
Yeah, so that the forecast without temperature, it included, and I didn't explain this. If you're interested, the paper is up online at Fish and Fisheries. The model without temperature has this autoregressive component across time, and so essentially it's the only thing that's giving it skill is the tendency for essentially density dependence. So in this case, a stock that is skewed further north than their historical distribution is likely on average to return to its historical average. Of course, that's not a very satisfying story in terms of multi-decadal distribution shift, but it probably is useful in terms of short-term fisheries management. And building in something like size structure would probably give you a little bit more skill. And frankly, density dependence and size structure are the main things that we use to have forecast skill in stock assessment. So it seems reasonable to think that if we're going to do forecasts of spatial ecology over the short term, some of those same mechanisms would probably help us with skill.
Okay.
Hi, Jim. It's Tara here. So thanks for that. It was kind of sobering, but also refreshing in a way. In your points about insufficiently testing model forecast skill is a very pertinent one. So when you think of the plethora of projection models that are now out there in the published world, are they worth the paper they're printed on?
I certainly think they are, and clearly this field is still developing. I think in a lot of fields it's useful to discriminate between strategic and tactical models, and I think a lot of the models that people developed first are strategic models that include a lot of the kind of a priori mechanism that makes sense. But I guess I caution that we don't often do short-term forecasts for setting quotas based on strategic models. Instead, we use a different class of models. And I guess I don't I'd really love to work with anybody about how to build new models that bridge that practical to strategic, and how to figure out which models are best for what purpose.
Yeah, because the analogy you drew to retrospective bias in stock assessments, I mean, the reason that that became so standard and widely applied is because the forecasts had real meaning in the real world, and were actually used to form the basis of advice. So, there's a constant need to check and evaluate, but maybe the same type of exercises certainly not being applied to the projections.
Yeah, and I really do want to distinguish between adaptation and mitigation strategies in climate. I mean, some of the stuff we're asked to give advice about is this multi-decadal mitigation, and we never want to lose sight of that, clearly. But I do think adaptation strategies occur on a much shorter time scale.
Hi, Jim. This is Melissa. I was kind of interested in hearing you talk about the fact that you could specify and estimate proxy reference points from VAST now, and I'm wondering, you're trying to bridge the divide between tactical and strategic advice. Have you compared the estimates that come out of VAST with, what has actually come out of stock assessments and been used to provide advice?
Yeah, I did, and I forget. I assume I did look at it briefly. The short answer is, I was working on that reference points in the last 3 months, so I'd love to do more comparison. Of course, having this an operating model hopefully would also allow us to compare, spatially explicit and spatially implicit models of fitting the same data. But yeah, good point that I should go back and double check what those would look like compared to the assessments for the species in the Gulf of Alaska.
Yeah, that'd be interesting.
Yeah.
Okay.
Yep.
Thanks, Jim. This is Alan. I'm excited that your paper is here because I've been frustrated with the climate envelope work for a long time because it's really kind of produced some counterintuitive results regionally. But I think, like in the National Climate Assessment in a number of locations, it's the only thing that exists where it's basically it's a backdrop global model. So, but that's been regionally extended. But as we see, it gets worse than persistent results in this comparison. And I guess it's kind of a question or something like to me, I think that it's sort of a case where someone smart person did a global analysis that's interesting, but then it's really persisted for a long time as the backdrop model that is being seemingly misinterpreted many times. And I guess the question is, so what do we do in light of, here's one sort of specific example, but I feel like it's sort of hard to disprove that kind of a study in a systematic way, and then it continues to have a big policy impact.
Yeah, and honestly, I don't think there's any way to do this except have the whole community do more skill testing and comparisons, because I think in any of these there's sort of an analyst effect, at least potentially, and probably in the literature. And I actually thought about doing more of these, and I decided not to because I'm really hoping that other people do more skill testing independently of me.
Yeah, one thought I have, it'd be interesting to do a literature review and see how many of these forecasts actually have confidence bounds on the forecast. Just describing the structural uncertainties in these forecasts would be a good step.
Yeah, no kidding. Yeah, and we also talk about ensemble modeling. You bring up structural uncertainty and, comparing different methods even without some skill testing metric would be nice, I think.
Jim, it's Myron Peck. I don't know if you can hear me. Probably doesn't matter.
Yeah.
So I'm just wondering if you've communicated with FishMap because of their number of global models that they're comparing using the same outputs, and also now they're doing comparisons between the global models and the regional models in their projections. Do you know FishMap?
So, no, I don't.
Okay. Yeah, we should put you in touch. I can put you in touch with that group. I think they'd be interested to chat with you because Tyler Eddy and I think there's 7 global models now, including William Chung's and a number of people around the world, and then a number of regional modeling hubs. And these are actually really important to the work that SIGME is trying to do, which is the Strategic Initiative on Climate Change. That's ICES-Pisces group. And so, and there was a presentation and a workshop at the last meeting in June in Washington, D.C., and they started comparing these global models and regional models, and the agreement was really, really poor. And they didn't get much further than that, but there were a lot of people with their mouths open in the room just going, oh my goodness, how do we know what's right, and what's not? And I was just wondering if you had ever thought about the global models versus regional model comparisons, whether you've ever attempted that, because I've always heard people say, well, you don't want to look at the North Sea when you have a global model, because the global model was never designed to do that. And then I was like, well, but if you can look at the North Sea, then what can you look at, or what should you look at? I mean, I was just wondering if you ever thought about the spatial scale of these models.
Yeah, I would love to collaborate on that. My short-term goals are to integrate more with the Alaska Climate Project, a climb that Kirsten Holzman and Ann Holloway are involved with, and that they're involved with some of the same people you're talking about. And then in my other life, I worked with Andy Rosenberg and people doing these kind of global versus regional model comparisons for stock assessment. Because the FAO wants to do all these data core. Sophia report analyses, and where I fall out is that it's really good to have all these different models, and really I'd like for us to have sort of like a registry of model results, where we can compare different models, and ultimately we ended up publishing, Sean Anderson led a paper about super ensemble modeling, which is what climate people do, where they come up with all their different methods, and then they compare them for some, again, basically using skill testing or a simulation design, and use that to, develop a model that combines those multiple models in different places. And, maybe it would come up with the fact that global model X is good in the Arctic and global model Y is good in the tropics. And
great. Here's Tara.
Yeah, I'm embarrassed to ask this question because you must already not sleep at all to generate so many models. But I'm just curious. I remember an offhand comment by a terrestrial ecologist in our school that they had real concerns about climate envelope models, and I was just wondering if the terrestrial ecology, whether they come to similar conclusions. Do you happen to know that literature?
Not very well. Like I said, my closest link in that world is Map of Life project. So Walter Jetz and Corey Marrow, and they do this similar kind of multiple data types, data integration worldwide kind of activities, and I do think that the best they often have is museum records and climate envelope models, and and then I think the path that they've been terrestrial ecology's gone down is what's the scale of response, what's the how to do integral projection models, size structured models with specific stages impacted, and I guess I'm kind of hoping that we can build some of those same IPM and multi-scale responses into these in the past. Maybe all I'll say is that just because I don't know if I have another slot to come in, if there's another general discussion, I'd be happy to call in, and I'd love to, like I said, I'd love to collaborate further with anybody who's interested in this stuff.
Yeah, I think there's going to be several chances this week. Actually, right now, the reason we're kind of going on and on about this and giving you all these questions is because we're actually going to be moving into a kind of a plenary discussion about not only your talk, but the other talks we heard this afternoon on kind of methodology, so you're welcome to stay on the line as long as you want.
Yeah, that's great. I'll stick around for a bit. Yeah.
But I have kind of a question, another one. One thing that came up this week is that, sometimes you have, and this is kind of like the Bering Sea, Northern Bering Sea example, you might have a stock that's moved from an area that's pretty well surveyed to an area that is, has limited survey data. And I think I was telling Greta Pessel that you had a paper on this and that you applied, at GIMIS, I think you used it as assessment as an alternative, to get some density estimates, model-based density estimates, for the Northern Bering Sea area. I think that might be of general interest to the group. Is that out yet, or I guess Jim? Yeah, go ahead.
Yeah, so I think the best place to look is that SAFE report, and I'm trying to figure out how to package it as a paper. Paul Golder and Colleen Minto and I have a scientific reports paper where we combined all the different data we can get for the Celtic Sea. And, we did the same, I think we did the same thing for the Gulf of Mexico with our no Bruce, where the Gulf of Mexico has something like 60 different biological sampling programs. A lot of them are just a single estuary. But, there's a few that don't span the whole thing, but do line up with each other. And, I personally, I do really think that sort of data synthesis and archiving of fishery-dependent data, in multiple data types, including museum records. I think that's the direction terrestrial people that I've worked with have gone down. And I hope we can get into that better in the ocean too.
Okay. Well, any other questions for Jim on his talk before we kind of move into the general discussion?
Hi Jim, this is Paul Fernandez at the University of Aberdeen. I'm wondering if in your modelling you make any distinction between interpolation and extrapolation, if you know what I mean, where it's related to the previous question, where your data is informing your modelling process within the range of, for example, the correlation or regression, whatever you're using to look at spatial continuity, as opposed to where you really are going into areas of weaker relationships to other covariates or weaker data points in the first place.
Yeah, unfortunately, essentially the model is no. The model kind of assumes that data are, the design is ignorable, and so, doesn't distinguish between, in any structural way, between areas with and without data. But, we are doing, we and others are doing research about non-stationary spatial models, and so you could imagine a case where, the properties linking a covariate to the process or the spatial correlation varies as a function of location, or, in which case, if you don't sample an area, it's a much bigger deal. So that's an active area of research statistically that we're hoping to build in.